Assalamu alaikum wa rahmatullah. Today we'll continue this chapter. We'll talk about orthogonal bases and complements. A basis set or a set of basis vectors like this one is called orthogonal if the inner product of any two basis vectors equals to 0 if they are different from each other. If are the same thing, so it will be it will give, so say if the case when I equals j, what we have, this equals to the norm squared of the basis vector. Okay, now if we apply another condition saying that then the norm squared equals to 1, this means that the basis set or set of basis vectors will be called orthonormal basis vector, and this is the same condition as 2.23. so we say that inner product of the basis vector with itself equals to 1, or in other words, the norm squared of the basis vector equals to 1. So if the two conditions 222 and 223 are satisfied in a set of basis vectors, then we call it an orthonormal basis. Okay, it's very useful, it has very nice properties, and we like to use it to represent data and vectors in general. Okay, so let's say that we have a vector space V and we have a subspace U of that vector space. Now we define what we call an orthogonal complement U perpendicular. So say this thing here, okay, U perpendicular, which is actually it is the subspace that is orthogonal to the subspace U. So we can say that, roughly speaking, that U is orthogonal to U perpendicular. This means that all vectors in U are orthogonal to all vectors in U perpendicular. Okay? Fine. So we can state several more facts about this pair of subspaces. Let's say that the overall vector space is V and U has m dimensions, so U perpendicular must have d minus m dimensions, and as we said earlier, there is nothing common between U and U perpendicular. So what will we gain from this definition by knowing or using the orthogonal subspace? So we say that any vector in the vector space, the original vector space that contains both of them. So if let's say that we have this vector space V, this vector space contains U, okay, and contains U perpendicular. So if we just draw it here, this is U perpendicular. Okay, so let's say that X belongs to V, so we can analyze X into two components. The first component belongs to U, to the orthogonal basis, and the rest of the components of X belongs to U perpendicular. So it's just like we're analyzing, we're disjointing X into two components, the main one and the perpendicular one. Okay, this will prove to be very useful, especially in regression in general. Okay, so here we have the basis vectors of U, and the B perpendicular are the basis vectors for U perpendicular. Okay, So here we have an example. See, so we have here, let's say that this is V. So V is actually the V is the 3D space. Okay, so let's say that U is a subspace of R2, right? So you see here, U is just plane. Okay, so what is U perpendicular is the rest of V. So it's everything in V, not in U. Okay, everything V, not in U. So both of them, so we can say actually that both of them in some cases they will build up or constitute the original vector space. Okay, fine. Okay, here what do we gain from this decomposition into subspace U and its complement, as we said before, the perpendicular subspace? I will say, okay, that any vector, say W, will have two components, one in U and another one in its complement. Okay, so I think we can look at here. So this is the vector W. Okay, so W belongs to V, right? It belongs to the 3D space. So so this should be R3, right? So here you can see that we can find a component of W that belongs to U. So let's change the color. Let's make it orange, right? So we have this let's say W here, okay? And we have the orthogonal complement of W. Let's put it in different color, say green. Yeah, so we have this one here. So we have this vector and this vector. So let's call this one, this would be W perpendicular, and this will, let's say, let's put it in orange. So this would be W, let's say, WU, okay, and this is W perpendicular, right? So this is U. So this belongs to U. Again, U. Okay, this is U. So now W is decomposed into two components. One belongs to the vector or subspace U, and the rest of W belongs to its complement. Okay, fine. So how do we do this decomposition? We do it by projection. So we project, as we saw here. Actually, this W U is the projection of the original W onto the subspace U, and W perpendicular is the projection of W onto U perpendicular. So now we need to learn about how to perform projection. Okay, so projection is a mapping from the original, or let's say the big vector space, into some subspace. So here we should say that we said it here that U is a part of V. So U is a subset of V. Okay, So this linear mapping, right, it's a linear mapping, has some nice properties. So we said that this projection operator or mapping is denoted by pi. So pi squared, which is performing pi twice, so you project the same vector twice into the subspace, equals pi. This might be a bit vague. How can we understand it? By we going up to this example, right? So let's say, okay, so let's use another color now. Let's say that we are using color this. Okay, now we use pi and w. Pi projects w into wu. So the purpose of pi is to project w onto u. Okay, so we get this w u vector. Now we want to apply pi again on this one, on this vector. So the job of pi is to project the vectors onto u, but if the vectors are already in u, so it doesn't change. So this is the whole idea. If the vector is already inside or lives in u and you project it onto u, you're not doing anything. Okay, so here says that it's enough to project the vector once. You don't need to do it twice. So you can also say that, okay, if we, let's change that, go back to the original color, right? So let's say that we want to say pi q. This means that I'm doing pi 3 times. This equals pi, right? Because I'm already projecting a vector that lives in u. Okay, so pi is a linear mapping. When we say linear, then we should know that we can represent this mapping by a matrix. This matrix is denoted by P, the projection matrix, and pi, the mapping that we're using. So this statement 2.25 is translated in linear algebra terms that pi p sub pi squared is p sub pi. Okay, so those two are equivalent. Fine. Okay, now let's say that we have a subspace U spanned by B1 and B2 like we have here, right? So actually it is spanned by E1 and E2, right? So this subspace U is spanned by E1 and E2. Okay, now when we project the vector onto U, then it lives in U, so it can be represented by basis vectors, right? But we still have this orthogonal complement or orthogonal component that lives in the complement subspace. Okay, so let's take a simple example, which is we want to project a vector on a one-dimensional space or subspace here, right? So it's actually this. Okay, so we have this vector x. So let's say here x. So what is the main vector space? V. V is r squared, right? This is the plane, the 2D plane, and we want to project it onto this subspace U, which is the line. Okay, how do you do this projection? We find the closest distance between x and its projection. So you can think about it, it's actually the shadow of x on the vector b. Okay? What is b? b is the basis of u. Since u is a one-dimensional subspace, we only need a single vector to represent it, which is vector b, right? So now what we need to find here is this projection. This means what? This is, let's write it down. So there should be an arrow. This is the projection of x, vector x, onto subspace. Which subspace? Subspace u, the line. Okay, so if we think about it here, this projection, which is another vector, so this pi of u, pi subscript or sub u of x is actually another vector. Since this is another vector that lives on u, it must be represented by b. So we can say that this new vector, the projection of x onto u, is actually, it is a representation by b, by multiplying by some constant pi. So now we know the form, the shape of this projection. What is unknown is lambda, okay, which is actually this length, the length from here, from the origin to this point, right? So this is the length, the constant that we multiply by a basis vector, right? Okay, another thing that we need to look at is this, right? This is the complement, this part, right? This is the complement of the projection, which lives where? In lambda and in u perpendicular. Okay, so a very nice property here is that if you take the difference, which is the difference between the projection, so let's write it in a neat way. Okay, so let's zoom in a little bit and write it. So this is actually the projection of x into u minus the original vector, right, which is this red dashed vector. This is perpendicular to the projection itself. So this is a very useful fact, right? And you should note that this fact also applies to multi-dimensional cases, so not only for when u is just a line, right? So it can be anything, u can be anything, right? For example, this case when you have a two-dimensional subspace, so we have a right angle here, right? So this is the projection and this is the difference, which is actually what? It is orthogonal, perpendicular to the projection, right? And this is what we talked about. The vector x is, it has two components. One, that can be projected, or it is projected on u, and the rest of it belongs to u perpendicular. So this looks like a v. This is u perpendicular. Okay. Fine. So let's return back to our simple example. So the way that we find this unknown lambda is saying, okay, we know that the inner product of the complement with the basis vector equals 0. Why? Because if you look here, as we said, this is the difference here. This is perpendicular to the basis vector, meaning that if we take the inner product, it is 0. Let's say that we're taking the dot product in the Euclidean space, right? So when you simplify this expression, the first thing that you say, okay, we substitute lambda b instead of the projection, right? And then we use the bilinear property of the inner product, so we actually distribute the terms here, so we have two inner products. Okay, now we have this is known, and this is known. What is unknown? It is lambda, so we can solve for the unknown, right? So we have a single equation with a single unknown, so lambda becomes this nice equation, right? So in the numerator we have the inner product of x with the basis vector b, and in the denominator we have the norm of the basis vector. Okay, so this is lambda. Okay. Now if you want to write the whole vector, right, it is actually this is what? This is lambda, right? And this is the basis vector. Now here we substituted the inner product with the dot product. So this is a special case, right? When we're talking about Euclidean space or vector spaces, right? Okay. Now we can rewrite this equation by using the projection matrix. Okay. How? Say, okay, the projected vector is actually a linear mapping of the vector itself using the projection matrix P sub pi, which equals lambda b. Okay, so if we rearrange this, so we say, okay, since lambda is a square, I can multiply it from the left or from the right. Okay, if I do it from the right, I can put it in this form, right? Remember that this is lambda. So if I put this lambda here on the right hand side, I get this one, right? Okay, now if I rearrange those two and put them in this form, b transpose, this is a matrix. This is if you remember, this is the outer product, right? Outer product in contrast to the inner product. Okay, outer products, and this is a matrix divided by some constant, and this is our vector that we want to project. So the projection matrix in the one-dimensional case is very simple. It's equation 2.33. Okay.